Hi everybody. So today we're gonna talk about modular arithmetic, introduction to modular arithmetic. We're gonna be looking at Fermat's theorem, Euler tangent function, Euler's theorem, and Wilson's theorem, and in general, like simple basic concepts in modular arithmetic and manipulation with modular arithmetic. So I guess let's kind of like review some of the material that we studied in the past. So a couple things about modular arithmetic. So we usually say that, A is congruent with B mod n. What does this mean? It means that both A and B have the same remainder. So basically A has remainder R and B has remainder R mod n, right? So both of them, if you remove R from them, they're going to be divisible by n. So what does that mean? Well, basically it means that A is going to be congruent. So basically A minus B is going to be congruent with 0 mod n. So it means that, n is divisible by a minus b. So basically, if a and b have the same remainder, right, when I take a minus b, the remainders are going to cancel out and n is going to like divide both of them. Okay, so this is basically, some simple rules about modular arithmetic. And then, of course, we have some like simple stuff that if I had, that a is going to be congruent with b mod n, and let's say that, c was congruent with d mod n, then basically what I can do is I can add them, I can subtract them, they're gonna like still be congruent, right? So I can do a plus or minus c is gonna be congruent with b plus or minus d mod n. And in addition, I can actually also multiply. So I can also say if I multiply them, so a times c is also gonna congruent with b times d, and all of this is gonna be congruent with basically r1 times r2 mod n, right? So if this has some remainder r1 and this has some remainder r2, then basically, if I were to, I guess I should write plus, minus, or multiplication of the remainders mod n. Okay, so this is basically some simple stuff with like, addition, subtraction, multiplication. Now, the more interesting case is basically the division. What's happening when I have division? And basically, if I want to simplify by something. So let's say that, a times some number t is gonna congruent with bt mod n. So when this happens, the question is, can I cancel like t on both sides? Can I just like remove t here and remove t here and basically say that a is gonna be congruent with b mod n? The question is, can I do this or not? Well, I guess let's look at a couple examples. So what would be a couple examples in here? When can I do the simplification? When I cannot do the simplification. So I guess, let me write down some examples. So let's think of something. So maybe is going to be congruent with, so let's do mod. What mod should we use? So I guess we can use mod 5 maybe. So I can write some stuff like this. So 22, for example, is going to be congruent with, 12 mod 5, right? So, okay, so this is clearly the case. So, well, I guess what can I do in here? So if I come and if I simplify stuff, so if you look at 22, it's going to be, 2 times 11 is going to be congruent with, I guess, 2 times 6 mod 5, right? So if I come and if I cancel the 2 on both sides, I get that 11 is going to be congruent with 6 mod 5, which is basically true, right? So 11 is actually congruent with 6 mod 5. So this is fine. But let's look at another example. For example, 22 is going to be congruent with 12 mod 10. So now what's happening if I write it 2 times 11 is going to be congruent with 2 times 6 mod 10, right? So now look at this. If I come and if I cancel 2 on both sides, if I cancel 2 here and 2 here, I'm going to get 11 is going to be congruent with 6 mod 10, and this is clearly wrong, right? So this is wrong. So basically, what do we notice in here? Sometimes modular arithmetic works, sometimes modular arithmetic doesn't work. Well, and why does it work here and why it doesn't work in here? The reason is basically the simplification here. If you look at this, we simplify by 2, which is fine. But in here, when we simplify by 2, we can't really simplify by 2. Well, why is that the case? Well, let's look at this. If I were to simplify, when I have something like this, right, what does this mean? It means that, 5 has to divide our difference, 22 minus 12, which is basically 2 times 11 minus, so basically, 5 has to divide 2, 11 minus 6. And now look at this, because 5 and 2 don't have anything in common. I can come and I can basically simplify the 2. So simplifying the 2 in here, it just means I simplify the 2 in here, and I get that 11 is congruent with 6 mod 5. But in this other case in here, when I look at 10 divides, 22 minus 12. So 10 has to divide 2 times, 11 minus 6. If you look in here, I cannot cancel by 2, because if I cancel by 2, I also need to cancel a 2 in here, because if you look at 10, 10 is actually equal to 5 times 2. So if I were to cancel, a 2 in here, you see that this 2 helps this 2, like this 2 is divisible, this 2 is a divisor of this, and the 5 is a divisor of this. So basically, if I wanted to, to cancel 2, I would need to cancel a 2 in here. So actually, when I cancel a 2 in here, I would also need to take 10 and divide 10 by 2 as well to be correct. So this is basically the problem, is that 2 and 5 are good numbers in here, right? So 2 and 5 are a good pair, so I can cancel the 2 in here. But in here, 2 and 10 are not a good pair, because 2 and 10 have some common factors, right? So I cannot cancel it. So I guess let's briefly review what are like good numbers, what are good pairs. So if you recall from the past, basically, if A comma B is equal to 1, what does this mean? It means that A and B are relatively prime. And when they're relatively prime, we call this a good pair, right? So they're like coprime, relatively prime, good pair. So different names we can use. Coprime, relatively prime, relatively prime. I like to use the name good pair, good pair. So now what is the benefit of like good pairs? Well, good pairs, you're gonna see in a moment, is like you're allowed to do simplifications in here, but there's actually like more stuff to good pairs. So now I guess if we go back to our example, so let's say that we had a good pair. So let's say that we have a good pair, and let's say we have a bad pair A and B. So the question is, if I have a bad pair, can I convert a bad pair into a good pair? So let's say that A comma B is equal to some number D. So this is basically bad pair. Well, then what can I do with this bad pair? Turns out every bad pair can be made into a good pair, because D is a common divisor. I can basically say that A, so basically I can do something like this. A is going to be equal to some A0D, and B is going to be equal to some B0D. And now if I were to write this again, A comma B, this would be the same as, A0D, B0D is equal to D. So basically I can just remove this, right? So what can I do in here? Well, I can actually cancel the D. So I can cancel D, D, and D. And then I'm basically going to be left with 1. So basically, if I started with a bad pair, AB equals D, I can just remove the D, and I can just write it like this. A0, B0 is equal to 1, which is basically, A divided by D, B divided by D is equal to 1. So basically, you see what's happening? I can take this D and I can divide it by D here and divide by D here and then just get 1. So if I write this divided by D, this divided by D, then this is basically equal to 1. Okay, so this is kind of like an important thing to keep in mind. So good pairs are nice. You're going to see nice properties of good pairs. But if you have a bad pair can always be made into a good pair by removing the bad stuff, by dividing by this D, right? When I divide by D, I'm going to be left with a good pair A0, B0. This good pair, bad pairs have other interesting properties. So let's say that, like I have a good product. So what do I mean by good product? Basically, imagine I had, that A, B, and N were a good pair. Well, what does this mean? Basically, if AB is good to N, so if AB is relatively prime to N, if this is equal to 1, then basically you're gonna get that both A and N is equal to 1. And B and N is also equal to 1. So basically, if AB is good to N, it means A is good to N and B is good to N. Well, why is that the case? Well, because, suppose, one of this wasn't good. Maybe A and N had some common factor D. Then what you can see is this is going to be divisible by D. This is going to be divisible by D, which is going to mean that, this is divisible by D. Well, and then this one's going to be divisible by D because, D is a factor of A. So D is definitely a factor of AB. So clearly, this wouldn't be able to be 1, right? Like if both AB and N are divisible by D, then, 1 also had to be divisible by D. Like the greatest common divisor has to contain at least D in it. So clearly, if AB is good to N, then this it has some like, is also going to be good to N. Yeah, so basically, yeah, if this is good, all of this have to be good. Now, how can we go the other way? If A is good to N and B is good to N, how can I show that AB is good to N? Well, assume that AB is not good to N. Well, if AB was equal to some X, right? Then this X thing, well, N would need to divide X and AB would need to divide X. Well, so let's look at X. Well, this X is going to be made out of like, I don't know, like maybe has like, if I look at X, well, if X divides AB, well, then there's going to be some part of X is going to be some part of X, a part of X is going to divide A and a part of X. So the thing is, well, let's think about this X. Well, if I had some number X in here, well, then let's write this X as like, I don't know, like some number, some prime number. So let's say this X is equal to some prime number. Let's take a prime number out, p times some c, right? So take the smallest prime that's in x, right? P, c. Then what do you see? Well, this is gonna be divisible by p, and this is gonna be divisible by p. Well, if ab is divisible by p, well, at least one of them has to be a multiple of p, either this one or both, right? So without lots of generality, let's assume that it's a. You know, if a is divisible by p, n is divisible by p, you're gonna get here that a is divisible by p, n is divisible by p. So what this means is like one has to be divisible by p. So basically p has to be 1 in this case. So we just, you know, proved what we needed to prove. If this two, if a and b and are good, then ab is also going to be good to n. So this property basically goes both ways. So, you know, if you had this two, you can also get this property. So you either have, if this is satisfied, then these two are satisfied. And if these two are satisfied, then you get this one. Okay, so this is some properties of the good numbers. Okay, so now why are this helpful? Well, now if we were to get back at this example with the division with modular arithmetic, well, we saw that, you know, 2 and 5 were good to n. So because 2 and 5 is good, see, 2 doesn't have any factors with 5, I can remove the 2. But in here, you know, when I looked at like 10 and this difference, I saw that 2 and 10, they have common factors. So if I cancel by a 2, I would need to cancel by a 2 in here. So let's actually like make this like more general. Let's use, you know, instead of using numbers 1, 2, 3, 4, let's use notations A, B, C. And let's prove just the general case of this property in here. So how would we prove this thing? Okay, so I guess let's see. So let's suppose that, you know, AT is gonna be congruent with some let's say BT mod n, right? Then what can I do in here? Well, both of them are going to have the same remainder, mod n. So n has to divide the difference, right? So I can basically say that, you know, n in this case is going to divide the difference, AT minus BT. So basically, you know, n has to divide the difference t, a minus b. Now look at this thing. If n and t were to be a good pair, if n and t were to be a good pair, right? If n and t don't have any common factors, then I can come and I can just remove the t in here. And I would get what? I would just get that n divides a minus b, which means that, you know, a is going to be congruent with b mod n. So basically, you know, if n and t are good to each other, then I can just cancel the t, right? So I can just cancel the t, and I'm going to get a is going to be congruent with b mod n. Okay, so this is fine. So it turns out that if, you know, if I have good, you know, good pairs n and t, then if t and n is good, I can cancel the t. Well, but now let's suppose that we are in a case where they're like not good, right? So let's suppose that we are in this case of like AT, BT. So let's say something along the lines of, you know, AT is gonna be congruent with BT mod n. But let's suppose that T and N are not good. So like basically N and T, they have some common factor D. Well, then what can we do in here? Well, if n and t are bad to each other, we can take the bad stuff out, right? Like this d, we can take it out. We can say that, you know, n is going to be equal to some n0t. So something like along those lines, n0t and t, sorry, n0d, right? And t is going to be t0d. So if I take these things and if I were to plug them in here, what would I get? I would get something along the lines of like, you know, n0d, t0d, gives me the common factor d. So I can just come and I can remove the d from everywhere, right? From here, here, here. And then basically I would end up with what? Basically I would end up with like, you know, n0, t0 is relatively prime, right? So basically I can start with, you know, a bad pair. So this is, you know, bad. So this is, you know, a bad pair, right? So bad pair. And then basically I'm going to be left in the end with a good pair, right? So I can take any bad pair, I can convert it into a good pair. Okay, so what is happening in this case if I were to do that? Well, you see that let's just write down the t. So I guess if I were to rewrite everything right in here with like, you know, what's good, what's bad, then basically what would I get? So I would have something along the lines of like, you know, a t0 d is equal to b t0 d mod n0 d. Okay, so now what does this mean? It means that this number has the same remainder as this number, this mod. So I can, you know, n has to divide the difference. So n0d has to divide the difference. So let's just like do that, right? So basically what do I get? I get that, you know, n has to divide at minus bt, which is, you know, t times a minus b. So I can, you know, I can rewrite this thing as like, you know, replace n with n0d. So n0d has to divide, I don't know, I guess t0d a minus b. So now if you look at like this thing, what do you guys notice? First of all, you know, d is on both sides. So if I were to cancel d in here, I would also need to cancel d in here because this d is a divisor of this d. So, you know, if this number divides this number, if I were to cancel the d in here and the d in here, I would get that n0 divides t0 a minus b. But now look, n0 and t0 are a good pair. They don't have any common factors. So if they don't have any common factors, I can come and I can uncancel also like t0, right? So basically, what I'm trying to say is you get this. n0 divides t0 a minus b. So now basically you can come and you can remove the t0 because t0 is good to n0. So the thing that you're left with is you're going to be left with n0 divides a minus b. Well, but what does this mean? It means that, you know, a is going to be congruent with b mod n0, right? So yeah, basically this is, you know, how it works. So if you started with something along the lines a t0d is going to be congruent with b t0d mod n0d, you need to look at like what's the bad stuff in here. The bad stuff in here is the common divisor d. So you can come and you can cancel d everywhere, but then you're going to be left with t0. But t0 is going to be good to n0, so you can always cancel the t0, right? So then you're going to be left with, you know, a is going to be congruent with b mod n0, which is basically n divided by d, right? Okay, cool. So basically this is how division works. So the division is really nice when you have, you know, you have good numbers. You have to work with good numbers. So if you were to look at, you know, this example in here where, you know, n and t are good to each other, you can just cancel the t, right? But if n and t were to be bad to each other, right? If n and t are bad, well, you can just take out the common factor d and make them into a good pair and then use the same property, right? When you take out the common factor d, it's going to be in here, you know, n is going to have a d and t is going to have a d. So you can just, you know, cancel d on both sides. And then you just have the normal property that t0 and n0 are good to each other. Whenever they're a good pair, you can cancel them. So then you just get this property in here, right? So if we were to go back to our example, our original example, what we notice? We notice that 2 and 5 are good to each other, right? But when we look in here, 2, 11, 2 times 6, actually what we see is that this is congruent with, you know, 10. Well, 10, but 10 is, well, so if I were to do it like this, 10, which is, you know, 2 times 5, right? So actually, if I were to come and if I were to cancel, you know, a 2 in here and a 2 in here, I would also need to cancel the 2 in here. So the way this simplification would work is that, you know, after I cancel the 2 in here, I'm gonna be left with 5, so that I don't have 10 here anymore. I'm gonna have a 5 in here. So basically, you know, this is how we fix this problem, right? Because, you know, 2 and 5 are like basically, you know, basically 2 and 10 are bad to each other. How are they bad? Because, you know, they both contain a 2. So you take out the bad stuff, which is the 2 in here, the common factor, right? Which is exactly what we did in this equation in here, right? Where we canceled the d on all the sides. Okay, cool. So this is basically kind of like an introduction to modular arithmetic, some simple properties that we can do. You know, we can, you know, the definition of modular arithmetic, and then we can add, subtract, multiply them. And then now we also saw that we can also simplify them, but the simplification works nicely. So now this is not wrong anymore. Now this is good, right? Good. Okay, cool. So yeah, so we saw that the simplification works nicely when a and b are relatively prime, basically when, I guess, when the thing that we want to simplify, t and n are relatively prime, right? Okay, cool. So this is, you know, nice properties about modular arithmetic. Now, what is another thing that we usually want to do with modular arithmetic? So one nice property is like, let's say that somebody asked you, what is the remainder? Well, actually, I guess one more little detail that I forgot to mention in here. Well, if a is going to be congruent with b, you also have another property that, you know, from here, you can also get another property that a to the n is going to be congruent with b to the n mod n, right? So mod. So actually, I don't really need to write it a to the n, b to the n. I can actually write them to any power. So we are already using n, so let's use k. A to the k is going to be congruent with b to the k mod n. So this is another property, right? Because, well, I can imagine I have a is congruent with b, and then another time a is congruent with b, and then just multiply them. And I'm going to get a squared is congruent with b squared. And then use a squared b squared again with an ab. So I'm going to get a cube with b cube. And then a to the fourth, b to the fourth. So you can keep going like this. You're going to get a to the k is going to be congruent with, you know, b to the k mod n in this case. All right, cool. So this is kind of like some interesting properties of, you know, modular arithmetic. So now where can we go with this? Well, so when do we need modular arithmetic? Well, we need it for a variety of reasons. Sometimes we're trying to solve equations. We're trying to figure out what's the structure of the problem. We're trying to show that an equation has no solutions. But another case where modular arithmetic is kind of like straightforward and really useful is, for example, if you wanted to compute the remainder, you know, how you have some big number and you're like, okay, what's the remainder of this big number, this modulus, right? Or for example, if you try to figure out what's the last digit of a number. So let's imagine I had, you know, 17 to the power 17. And the question is, what's the last digit? So find last digit of this equation. Find last digit, right? So how can we find last digit of this equation? Well, basically, we need to figure out what is this congruent to mod 10, right? Because if I had some big number, let's say 7, 5, 4, 9, 8, 2, 3, right? Something like this, a very big number. What is this gonna be? What's the last digit? Well, you see that the last digit is 3. Well, this entire thing is gonna be congruent with 3 mod 10. So basically, if I ask you, you know, what is a number congruent to mod 10, that's basically, you know, the last digit, because everything else besides the last digit, all of this is going to be a multiple of 10, and 3 is going to be the only like the last digit, which gives me the remainder 3 mod 10. So if I wanted, you know, the last digit of 17 to the power 17, how could I do it? Well, I could write it like this. I could write it, you know, what is this going to be congruent to mod 10? First of all, you see one thing right away. 17 is going to be congruent with 7 mod 10. Right? So because of that, I can actually, you know, simplify this a little bit, and I can say that this is going to be congruent with 7 to the power 17, but I still need to compute what is this going to be mod 10, right? Okay, so what could we do in here? So, well, so I guess one thing that we want to do is, we're kind of like interested, is there like some 7 to the power k that is going to be congruent with 1 mod 10? Well, why do we care about this? Because if you look at 7 to the 17, 7 to the 17, right? If you were to look at this one, 7 to the 17, you can write this as like, you know, 7 to the k times, you know, 7 to the k times 7 to the k, 7 to the k times 7 to some remainder. Well, and if, so now what are we going to have? We're going to have that, you know, this 17 is going to be a bunch of k's. So basically, you know, we're going to have that 17 is going to be equal to k times some number t. Let's say that I had, you know, t of this plus r. So if, you know, I need to figure out if I can find out, you know, what k gives me 1 mod 10, then what do you see right away? Well, you see that the 7 to the k is 1, this is 1, this is 1, this is 1. All of them are going to be 1. So this entire thing is just going to be congruent with 7 to the power r mod 10, right? So basically, you see, I had a big number 17. Now I can cancel all of this stuff, and I'm going to get just a 7 to the r mod 10. So actually, in our case, we can figure out quite easily what 7 to the k is going to be, because if you were to just like start with some simple small numbers, right? So let's say I had, you know, 7 is going to be congruent with 7 mod 10. But look at 7 squared. Well, 7 squared is going to be congruent with 49, which is going to be congruent with 9, which is going to be congruent with minus 1 mod 10, right? So mod 10. So mod 10, 7 squared is congruent with minus 1. Well, then what you can do is you can square this again. So whenever you get a minus 1, this is actually really nice, because you can take 7 squared and you can square this. So it's going to be, you know, minus 1 squared, which is just going to be 1 mod 10. So this is nice. So basically we have that, you know, 7 to the 4th is going to be congruent with 1. So I guess, you know, when I had 7 to the 17, what can I do with 7 to the 17? If I had 7 to the 17, I can write it as, you know, 7 to the 4, 7 to the 4, 7 to the 4 times a 7 to the 4 times a 7 to the remainder, which is 1. So this is going to be congruent with what? Well, I guess all these are going to cancel because they're all 1, right? So I just get, you know, 7 mod 10, 7 mod 10. So basically I'm done. So the remainder of, you know, 7 to the 17 is going to be 17 to the 17 is going to be 7 to the 17, which is going to be just, you know, 7, right? So the answer here is just going to be 7. Yeah, so basically this is kind of it. So now the natural question that arises is that, you know, when is 7 to the power k equal, you know, congruent with 1, some mod that we're looking at? So I guess in this case it was easy. We tried 7 squared, and we noticed we got a minus 1, and then we're like, okay, we're gonna square it. So, you know, you can do trial and error, just try multiple things, but maybe there is an easier strategy to achieve that. And turns out there is one. So in number theory, when you have to deal with prime numbers, this is called Fermat's little theorem. So Fermat's little theorem basically says that a to the power p minus 1 is going to be congruent with 1 mod p if a and p are good to each other. So if a and p are a good pair, so this is called Fermat's little theorem. But, well, you might say, okay, but how about the case when, you know, P is not a prime? So if I had some number n, any random number n, so this is mod, let's say some mod n, right? Then there is also another property, a to the power phi of n is going to be congruent with 1 mod n. And this phi of n is called Euler's function. And in here, we would want a and n to be good to each other. Yeah, and then we'd have, you know, phi of n. So what is phi of n? So phi of n is Euler's function. So phi of n is the number. So this is Euler's quotient function. Wait, so for now you don't really need to care about this, so you can just forget about this, and we're just gonna focus on this for now, and then we're gonna look at the second part. So I'm just telling you what I'm doing here is I'm telling you that there's special numbers, for example, p minus 1 when you look mod p, and phi of n when you look mod n, that if you raise a to that power, and if a is a nice number, like a is good to p, or for example a is good to n, because if a was bad to n, there is no way you can achieve something that's good, then turns out that these properties are going to be satisfied. So let's see how could we prove this theorems in here? How could we, you know, very quickly figure out, you know, some numbers that are going to give me 1 mod 10? But actually, I guess if we look at like a couple examples in here. So for example, if you were to work, let's pick a prime, let's say 7, right? So mod 7. So if I look mod 7, well, what this theorem is saying is that if you pick a number, so let's say 5, and it's saying that if you look at 5 to power 7 minus 1, it needs to be congruent with 1 mod 7. Let's see if this is true. Well, I guess 5 is just going to be congruent with 5 mod 7, right? Well, what about, you know, 5 squared? Well, 5 squared is going to be congruent with 25, which is just going to be congruent with, I guess it's going to be 21 plus 4. So it's just going to be congruent with 4 mod 7, right? Okay, so now what's next? I guess you see that there's 5 to the 6 in here. So if you look at 5 to the power 3, this is going to be congruent with 5 times 4. Or I guess I can write it as 5 times 5 squared, which is, you know, congruent with 5 times 4, which is congruent with 20, which is congruent with minus 1 mod 7, right? So now, this is nice because, you know, I got 5 to the 3 is minus 1. So what is the beauty of this? Because if I were to take 5 to the 6, which is going to be, you know, 5 to the 3 squared, this is going to be congruent with minus 1 squared, which is going to be congruent with 1 mod 7. Okay, so this is cool. So it turns out that Fermat's little theorem at least works for 5 and 7. So let's see if it works in general, because, you know, this is going to be something that we are going to want to be using in the future for like more complex numbers. So before we try to prove Fermat's little theorem, I actually suggest we look at a different thing. Let's look at like this special, you know, let's look at like, okay, what are the possible remainders, you know, mod 7? So if I were to look at possible remainders mod 7, I can, you know, clearly they're going to be 0, 1, 2, 3 all the way through 7. So basically the possible remainders mod 7 are going to be 0, 1, 2, 3, 4, 5, 6, right? So these are the possible remainders. So possible remainders mod 7. So let's call this set as 7 because, you know, these are the possible remainders mod 7. Okay, so now what is gonna happen if I take this set and I double it? So for example, if I were to look at the set 2 as 7, so basically what I do is I take all the remainders and I double them. So I'm gonna get 0, 2, 4, 6, 8, 10, 12. Well, what do you see about these numbers? Well, 0, so this set in here is actually gonna be the set 0, 2, 4, 6. But what is 8 mod 7? So remainder 8 is the same as remainder 1, right? And what about remainder 10? Well, remainder 10 is the same as remainder 3. And what about remainder 12 mod 7? Well, remainder 12 is the same as remainder 5. So actually, if you look at like all of these remainders in here and all of these remainders in here, what do you see? They're going to be the same remainders. These are all the remainders 0 through 6. These are also all the remainders 0 through 6, but they're shuffled. You have 0, 1, 2, 3, 4, 5, 6, right? So you got back all the same remainders. Let's look at another example. What if I were to look at the set 3s7? Well, if I look at the set 3s7, well, I just need to take and multiply by 3 all these remainders. So I'm going to get, you know, 0, 3, 6, 9, 12, 15, 18. Well, but if I were to look at like this remainders, you know, again, if I look at like this remainders mod, so let me use red color maybe. So I'm going to use red color. So what are these remainders, you know, 3s7, you know, this is going to be 2s7. Actually, let me also rewrite this with a red color because I just want to have it look more aesthetically pleasing. So it's going to be 0, 2, 4, 6, 1, 3, 5, right? So we notice that this remainders here is the same as like this remainders here. And also let's look at this. Well, 0 is still 0, 3, 6. But well, what is the remainder of 9? Remainder of 9. So remember, we're working mod 7. So what does a remainder of 9 mean mod 7? Well, this is just 2. Well, what does a remainder of 12 mod 7 mean? So, well, 12 divided by 7 gives you remainder 5. What about 15? Well, 15 is 14 plus 1, so it gives me remainder 1. What about 18? Well, it's 14 plus 4, so it gives me remainder 4. Wow, so actually, if you look in here, you see that all of these remainders, again, these are all the remainders, 1, 0, 1, 2, 3, 4, 5, 6, right? So this is the same as like this remainder. So it turns out that we get an interesting property in here. Turns out that, you know, the set S7, so the set S7 is going to be congruent with the set 2S7, and it's also going to be congruent with the set 3S7. Turns out that there's actually a more general property. It's going to be congruent with any set AS7. So if you take, you know, S7 and you multiply it by any good number, so one thing here, A and 7 need to be a good number. A and 7 need to be good. Well, what is the problem if A and 7 weren't to be good? Well, what is a number that's bad to 7? Well, if I were to pick A to be equal 7, right? If A is equal to 7, then clearly this is a bad one. So basically, if A and 7, what does it mean for A and 7 to be good? It means that 7 doesn't divide A, right? It means that A is not congruent with 0 mod 7. Well, why is that the case? Because 7 has only one possible divisor, 7 and 1, right? So like if their common divisor is not 1, then their common divisor has to be 7, so 7 would have to divide 8. But if A and 7 is good, then if this is satisfied, then turns out this is always the case, right? Well, what if, you know, I picked this set 7 and I multiplied it by well, what if I looked at the set, you know, 7s7? What would I get? Then you see I'm gonna get, you know, 0, 7, 14, 21, 28, 35, 42. And actually, one thing that you notice in here, guys, is that all these numbers are gonna be 0, right? What are like all these remainders? This is 0, 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 and this is 0, right? So basically, if I were to take this set and I multiply it by 7, or a multiple of 7, a number that's bad to 7, then basically I get like all 0, 0, 0, 0. So clearly this is a boring set. It cannot be equal to this. But if I take S7 and I multiply it by any other number, 2, 3, and in general, like any other number, turns out that I'm going to get the same set. It's just the remainders are going to be shuffled. So let's see if let's try and prove this property like more generally. Let's try and show that this is always the case. That basically, if I take any prime number and I look at the set SP, so what's happening? So I take any prime number and I look at the set SP. Well, what are the possible remainders mod P? It's going to be 0, 1, 2, 3, 4, 5, all the way until, you know, P minus 1. Let me do it like this, P minus 1. Well, then what I want to show is, I want to show that if I take this set and I multiply it by some number A, so if I look at the set, you know, well, first of all, let's take, you know, I want A and P to be good to each other, right? So if A and P are good to each other, what does it mean? It means that, well, what are all the possible divisors of P? They're 1 and P. So if A and P are good to, so if they weren't to be good, then the other possible divisor would be P. So it would mean that P divides A. If P divides A, it means that these are bad. But if P doesn't divide A, then it means that these are good, right? So basically, you know, A cannot be congruent with 0 mod P. So all these three statements, they're all equivalent. They're all saying the same thing, that A and P are a good pair, right? So if A and P are a good pair, well, then what can I say? Well, what happened if I actually picked a bad number? What would be a bad A to pick? Well, a bad A would be to pick if I make A to be equal P, right? If I were to pick A to be equal P, if I were to look at this set, P S P, then what would I get? You see that P multiplying by P is the same as looking at the set 0 SP, because, you know, you multiply by 0 and P are going to be congruent mod P. So if I multiply by 0, I'm going to get 0, 0, 0, 0, you know, 0, 0, 0. So this is just going to be the 0 set. This is a boring set. This doesn't give you anything nice. But if I were to take this set and multiply it by any other number, so if I were to look at, you know, the set ASP, which is, let's say, something along the lines, you know, 0A, 2A, 3A, 4A, 5A, you know, P minus 1A. And then, actually, let me do it like slightly like this. So let me clear this a little bit. And then P minus 1A. Then I claim that these two sets are the same set. So basically, my claim is that, you know, this set here and this set here, they're equal. So basically, you know, the set SP is going to be the same as the set ASP. The only thing that can happen is that these numbers can get shuffled around. So, but they're going to be the same number. Same way as in here, if you look at the set 2S7, this numbers in here, they're the same as this numbers here, they're just shuffled around. If you look at 3s7, again, the numbers are shuffled around, but I claim they're the same numbers. So let's try and show that, this set in here has the same numbers as this set in here. Well, how can I do that? Well, first of all, how many elements does this set have? It has p elements. It has all the possible remainders, right? It has all the possible remainders. So let's try and show that this set also has all the possible remainders. Well, this set also has, I guess, p remainders. So what I need to show is that these are all different. If all these remainders are different, in total, there is, p possible remainders. And if I have p remainders, and if they're all different, they have to be all the possible remainders, right? So first of all, one thing that we see right away in here is that 0 is already matched with 0, right? So what I need to show is that I need to show that these numbers here are the same as these numbers here. So actually, 0 is kind of boring. So we can actually remove 0 from here if I just like look at S star, SP star. So when I write a star in here, it just means that I remove the 0, right? Because 0 is kind of like boring. It doesn't do anything. So if I can show that these two sets are the same, right, without 0, then if I add the 0 back in, they're still going to be the same set. So if you look in here, what do you have? You have p minus 1 remainders. All the remainders, these are all actually good remainders, mod p. These are all remainders that don't give you 0, right? Like 1 through p minus 1. Well, if I show that these are all the possible remainders, all the possible p minus 1 remainders that don't give me 0, if I show that they're all different, then it means that they have to be all these remainders. Well, so first of all, so basically what do I have? So I have, well, let's write it here. So SP, so the size of SP is equal to, I guess, star is equal to, p minus 1. So is equals to, so SP star, it has size p minus 1, which is also the size of S, so A S P star, right? So basically the sets have same size. So same size. So basically what I need to show is I need to show all different. So the only thing that's left is like show all remainders are different. Because, in total, there can be p minus 1 remainders that are not 0. And if I show that all these remainders in here are all different and there's p minus 1 of them, they have to be this p minus 1 remainders. Well, how can I show that they're all different? Well, let's suppose that they're not all different. So let's suppose there's two remainders, like maybe there's some remainder Ka, and maybe somewhere here there's another remainder Sa. Now let's suppose that these two remainders are the same. Well, what would I have? Well, if Ka is going to be congruent with Sa mod P, well, then what do I have? So first of all, remember, A and P are a good pair. So whenever I have to deal with good pairs, I can always simplify the A, right? So if you look at like this example in here, that we just had, right? If T and N are a good pair, I can always cancel the T on both sides, right? So that's why I actually care about good numbers, because if A and P are good, I can come and I can cancel the A on both sides. And what would I get? I would get that K has to be congruent with S mod P. So basically, P, so basically P needs to divide K. So P has to divide, K minus S. So basically, but look at K minus S. Well, K and S are two numbers between 0 and P. But so this number K and S, if K and S are two numbers between 0 and P, the only possibility here is actually if K is equal to S. But if I picked, K to be different from S, if K is different from S, this is not possible. So this clearly like not possible, right? Not possible. Look, if I pick two numbers here, then what would I get? Clearly, K minus S, if you look at, an absolute value, or I guess I can, so let's suppose that S was greater than, let's say that S is greater than K, right? So I would clearly, get that, it needs to divide S minus K. But if you look at like S minus K, look, it's going to be greater than 0. It's going to be less than P minus 1. Clearly, I cannot have some number between 0 and P minus 1 that's going to divide P, right? So this is not possible. So not possible. So it means, so not possible. So this is not possible. So it means that, well, what does it mean? It means that, Ka is not congruent with Sa. So Ka is not going to be congruent with Sa mod P. So it means, what it means is that they're all different. They're all different remainders, right? So now what do you have? If they're all different remainders, and there is P minus 1 of them, and there can only be P minus 1 remainders. And if they're all different, they have to be exactly these remainders. So it means that this numbers in here, this set, A, 2A, 3A, 4A, all the way until P minus 1A, and this set, they have to be the same set. Okay, so this is actually the cool set as P, well, the one that has all the possible remainders. Okay, so now what is some interesting property that I can do with these two sets? Well, if they have the same remainders, so if I look at like, this set, so let's say yeah, so I have the set, 0, 1, 2, 3, all the way until, p minus 1. P minus 1. And if this set is going to be congruent with the set 0a, 2a, 3a, all the way until, p minus 1a, then I can do a couple things. I can add all the numbers in here. They have to be congruent with sum of all the numbers in here, right? So if I were to, sum up all the numbers in here, what would I get? So I'll get, 0 plus 1 plus 2 plus 3 plus. Well, actually, I can do more than that, right? Like, actually, if you look in here, 0 is kind of like in both sets, right? So I can actually remove. So if these two sets are the same, I can remove 0 from both of them. Let's remove 0 because 0 is going to be kind of like a boring number. It doesn't do anything. But if I were to remove 0, what am I going to be left with? So I'm going to be left with, like 1 plus 2 plus 3 plus 4 plus p minus 1 is going to be congruent with, I guess, a plus 2a plus 3a plus p minus 1a, right? Mod p. Because these two sets, they're congruent mod p. So mod p, they're congruent, right? So, well, what is the sum? This is, you guys can recognize this as a Gauss sum. If you take the sum all the way from 1 to p minus 1, right, then you see that if I put 1 and p minus 1 in pairs, they're all going to give you p. So actually, this thing in here, if you use the formula, it's just going to be p minus 1 times p divided by 2, which is going to be congruent with. And well, in here, if I take a in front of the parenthesis, if I take a in front of the parenthesis, what am I going to have? I'm going to have 1 plus 2 plus p minus 1, which is actually also going to be a times, well, what is this? It's going to be the exact same thing. So p times p minus 1 divided by 2 mod p. Well, but this is a problem here, right? Because, well, if you look at like this thing in here, well, what are you going to get? Well, you get that this thing in here, look, because I multiplied, this is even, right? So p minus 1. So actually, so if you look at this thing, what did I get? I just got that p times p minus 1 divided by 2 is going to be congruent with a times p minus 1 divided by 2 mod p. So if you look at like this thing in here, you see that because I multiply by p on both sides, p is going to be congruent with 0. So this entire thing is just going to be congruent with 0, right? Because, this is congruent with 0 here, and this is going to be congruent with 0 here. So it's basically the theorem is saying that 0 is going to be congruent with 0 mod p. So it turns out that, if I were to, add all the numbers in this set and all the numbers in this set, I don't get anything interesting. I just get that 0 is congruent with 0. And clearly, I cannot simplify the p, right? Because, well, I could, try to simplify this and this on both sides, but it still doesn't give me anything interesting because I still get 0 is congruent with 0. This is actually like usually a problem in modular arithmetic. For example, if you got, 7 times 0 is going to be congruent with 100, or like, let's say with, let's say this is going to be congruent with 12 times 0 mod 100, right? Because, well, clearly both of them are, for example, congruent with 0, right? But you cannot come, if you were to multiply by 0, you cannot cancel 0 and 0 and say that 7 is congruent with 12 mod 100, right? This would clearly be wrong. This is like, not possible, right? So that's a problem when you multiply by 0. So you don't want to get 0. So adding them doesn't result in anything useful. So now the question is there anything I can do, anything else I can do to these two sets, SP without the 0? That I'll get some stuff in here that gives me the same property for both of them. Well, it turns out there is another thing you could do. You could, for example, multiply all the stuff in here and multiply all the stuff in here, and you'd have to get basically the same thing, right? Because these numbers in here, they're going to be congruent with these numbers here in some like shuffled way, right? Same way as like these numbers here are going to be the same as these numbers here, the same as these numbers here. Like, all these sets are going to be congruent. So, this set here, this remainders here are the same as this remainders here. So if I multiply all the numbers in here, I should get the same as all the numbers in here. And you see why I leave 0 aside, because if I were to multiply everything here and also add the 0, multiply by 0, then it's all going to be 0. And in here, the entire product is also going to be 0 if I keep 0. So that's why I remove the zeros, because the 0 doesn't do anything. When I add them, 0 doesn't do anything. When I multiply them, it's actually worse. It turns everything into 0. So I don't want that. So if I were to look at just these two sets, and instead of adding them, what if I try to multiply them? Maybe multiplying them is going to give me something more interesting. And turns out that, yes, it's going to give you more interesting stuff. So if I look at the set, 1, 2, 3, all the way until, p minus 1, and I say that this set is going to be congruent with the set A, 2A, 3A, all the way until, p minus 1A. Well, then what's happening if I multiply all the numbers here? I'm going to get, 1 times 2 times 3 times p times, times 4 times 5 times p minus 1. Well, this is going to be congruent with what? Well, this product. How many a's am I going to have in here? I'm going to have p minus 1 a, so it's going to be So I can write it as like a to the power p minus 1 times 1 times 2 times 3 times 4 times, p minus 1 mod p. Well, but now look at this. What do I have? Well, 2 is a good number to p. So 2 and p are a good pair, right? They're equal to they're relatively prime. So I can come and I can cancel the 2 on both sides. I can cancel the 3 on both sides because they're also good. I can cancel the 4 on both sides because 4 and p is also good. Turns out that p is actually good to all of these numbers. It doesn't have any common factors with any of this, right? Like it's relatively prime to all of this. Like p with any number from here is going to be, relatively prime. So I can cancel all of them. 5 is going to cancel with a 5 in here. All the stuff in here is going to cancel with all the stuff in here. P minus 1 is going to cancel with p minus 1. So what am I going to be left with in the end? In the end, I'm going to get this, that a to the power p minus 1 is going to be congruent with 1 mod p. So now this property in here, this is called Fermat's little theorem. So maybe I should use a different. So Fermat's little theorem. So yeah, basically Fermat's little theorem says that if you take A, so keep in mind that A and P need to be a good pair, right? So like what we're doing in here, we're keeping A and P to be a good pair. If that wasn't the case, this clearly wouldn't be true. But this, if A is any number like this, then A and P are a good pair. If A and P are a good pair, then this works. So basically we need A and P to be a good pair, right? Equal 1, a good pair. So I need a good pair. So if I had a good pair, then turns out this is, always the case. So if you take a to the power p minus 1, it's going to be congruent with 1 mod p. Well, let's look at maybe a couple different examples in here. What are some examples we can do? So, well, I guess I can use p to be equal 7. So I tried p equals 7, one example in here, right? P equals 7, and I got 5, right? Well, let's maybe try a different example. What about 4 and 7, right? So if I were to look at 4 to the power, so let's say I want to show that 4 to the power 6, which is 4 to the power 7 minus 1, 4 to the power 7 minus 1, I want to show that this is also congruent with 1 mod 7. Well, how can I show this? Well, if I were to look at, 4 is going to be just congruent with 4 mod 7, right? Well, what about 4 squared? Well, 4 squared is going to be congruent with, I guess 16, which is congruent with 2 mod 7. So if I wanted, 4 to the cube, it's going to be congruent with 4 squared times 4. So it's going to be congruent with 2 times 4, which is going to be congruent with 8, which is going to be congruent with 1 mod 7. So it turns out that we are good. We got 4 to the 3 is going to be congruent with 1. So clearly, if I were to have 4 to the 6, this is going to be 4 to the 3 all squared, which is going to be 1 squared, which is going to be 1 mod 7, right? So yeah, you guys see that if you take any number and you raise it to the power 7 minus 1 to the power 6, it always gives you remainder 1 mod 7. So in practice, it turns out that it works. You can, you could possibly look at like other examples. So for example, if you were to pick p to be equal to, I don't know, like maybe 5, right? So if p is equal to 5, right? So if I had something along the lines of, p equals to 5, right? Then a to the power p minus 1 is going to be congruent with 1 mod p. This would basically tell me what? It would tell me that a to the power 4 is going to be congruent with 1 mod p. If a and p are a good pair, right? So if a comma p equals 1, so basically good pair, good pair. So if I had a good pair, well, what is a good pair for 5? I guess, you can pick, for example, 3. So let's try and show that, 3 to the power 4 is going to be congruent with 1 mod 5. Well, what is 3 to the power 4? Well, 3 to the power 4 is going to be congruent with 9 times 9, which is going to be congruent with, I guess, 81, which is going to be congruent with 1 mod 5. Right? Okay, cool. So see, if I try any numbers and I raise them to the power p minus 1, I'll always get 1 mod 5. So yeah, these are like some, simple examples to see that Fermat's little theorem works. But turns out in practice, Fermat's little theorem is going to basically work all the time. All the time is going to give you 1 mod p. Okay, cool. So this is Fermat's little theorem. Well, let's see, where could this be useful? So I guess turns out one example, I guess if you guys wanted to do some practice problems, let me maybe share my screen and show you some like practice problems. So give me 1 second. Okay, let's see. I guess these problems are a bit more complicated, but yeah, maybe we can do some practice problems. So let me do some share screening here. So for example, if we open Brilliant, so Brilliant again is an amazing website. They have a free wiki that you can access and like solve practice problems in here. So what is the problem saying? Well, the problem is saying that a to the power p is going to be congruent with a mod p. So there is actually, this theorem is the same as like our theorem, because in here there is actually two cases: a is good or a is bad. So if a is good, so if a and p are a bad pair. So let's look at two cases. A and p is greater than 1, right? So if a and p is equal to p, which is not equal to 1, so basically we are in the case of we have a bad pair, right? So if we have a bad pair, so basically, the case p divides a. So this is the case of like the bad pair. Well, if p divides a, then a is going to be congruent with 0 mod p, right? So basically, we're in the case where p divides a, which means that a is going to be congruent with 0 mod p. Well, if we're in this case of the bad pair, so in the bad pair, like all of this are equivalent, well, then all this means is that, this is going to be congruent with 0, and this is going to be congruent with 0. So they're both congruent with 0. So this is clearly true. But if we're in the case of a good pair, so let's say we're in the case of, good pair. So good pair. What does a good pair mean? It means that a and p are relatively prime. So it means that p doesn't divide a. So a is not congruent with 0 mod p. So if we're in the case of, the good pair, then what can I do? Well, I can cancel a on both sides, right? This is a to the 1, this is a to the p. I can cancel, an a on both sides. So if I were to cancel an a, this would become p minus 1. So I'd get, a to the power p minus 1 is going to be congruent with 1 mod p. So actually, I guess this theorem is like more general because it doesn't care if a is good or bad. This is always the case. And if a is bad, then this is always 0. This is 0 and this is 0. But if a is a good pair, I can cancel the a and I just can get the theorem that I just described to you guys. A to the power p minus 1 gives me 1 mod p. And oftentimes this is the one we care about. We're kind of like curious, can I find a quick power that gives me 1? Because if, I had some number to some big power and I asked what is this mod, I wanted to figure out, well, is there a power that gives me 1? So I can use that power to simplify stuff, right? Similar to, the example that we did with 17 to the power 17. So when we looked at, I guess, which example? We looked at this example and we asked, well, is there, some number k such that if I take 7 to the power 17, if I were to like take to the k power in here multiple times, is there, such a k that I can, cancel multiple times and then just be left with a remainder, some small number. And we saw that in this case with 7 and mod 10, this was 7 to the 4, right? So 7 to the 4 gave me 1, so I can write 7 to the 17 as 7 to the 4 multiple times with, a 7 to the 1 at the end. So then that gave me the answer. Because, the remainder is always going to be a number that's between 0 and k minus 1, right? If r it was something greater than k, then, you can take more 7 to the k's out of it. All right, okay. So I guess let's try maybe to do some practice problems in here, and then we're gonna go into like some more advanced concepts. So if I guess let's look at one more example. So the question is 11 is a prime? So here's another example. So for example, yeah, to the 10 is gonna be congruent with 1 mod 11. So here's the question. So what is the remainder obtained when this number is divided by 13? Okay, so this is kind of like tricky, kind of like hard, right? Because 2 to the 70, 3 to the 70, these are going to be some like really big, like really huge numbers. So then the question is, what are the possible remainders that you can get when you take 2 to the 70 or 3 to the 70 and you divide it by, 13? Well, luckily, we know because of Fermat theorem, I know that if I were to take, look at 13 is a prime. So if I were to take, a to the power 12, this is going to be congruent with 1 mod 13, as long as a and 13 are a good pair, right? So if a and 13 are relatively prime. So basically, as long as 13 doesn't divide a, as long as a is not a multiple of 13, this is always going to be congruent with 1, right? But, well, you see that 2 and 13 are going to be a good pair, and 3 and 13 are also going to be a good pair. So this is 1, right? So these are both 2 and 13, 2 and 3, they're both good to 13, so they're both, good pairs. So, if I were to look at 2 to the 70, I can write it as, this is going to be 2 to the 12. So I can write it 2 to the 12 times, 2 to the 12 times 2 to the 12, the multiple times 2 to the 12 times 2 to some remainder, right? Well, and what's going to be that? So this is all mod 13, right? Well, but what is going to be the remainder when I divide 70 by 12, right? So if I were to use a calculator, so, I'm going to take 70, right? So yeah, let's take 70 divided by 12. I got 5.8. So if I take 8 times 12, it's gonna be 96. Wait a second. So 5 times 12. Yeah, so I guess if actually if you look at yeah, actually if I write one more 2 to the 12 in here, you see that this is gonna be 2 to the power 60, right? So the remainder is gonna be 2 to the power 10. So the only the remainder that's gonna be left in here is gonna be 2 to the power 10. So basically it's gonna be congruent with 2 to the 10 mod 13. And the same story happens with 3. If I were to replace the 2 with a 3, I can write 3, I can write 3, I can write 3, 3, 3, 3, 3, right? So I'm gonna get that, 2 to that 3 to the 7 is gonna be congruent with 3 to the 10, right? So because this theorem here holds for both 2 to the power 12, and it also holds for 3 to the power 12 is equal to 1. So I guess you see, guys, what I'm doing. This is 1, 1, 1, 1, 1 cancel. So I get 2 to the 7 is gonna be congruent with 2 to the 10. Similarly, 3 to the 70. So similarly, I can do the same stuff for 3. So 3 to the 70 is gonna be congruent with 3 to the 10 mod 13. All right, cool. And now if I wanted, to get the remainder, I can say that, well, what's going to be the remainder in here? I guess I can say this entire thing is going to be congruent with, 2 to the 10 plus, 3 to the 10. And this is going to be congruent to, well, these are like now smaller numbers, right? So you can at least try to compute them, mod 13. So I guess if you wanted 2 to the 10, right? So if I wanted 2 to the 10, well, what can I say? This is going to be 8 times 8 times 8 times 8 times, I guess actually let's try and compute what is going to be 2 to the 10 mod 13. So let's try and do actually this one. So if you look at 2 to the 10, right, this is going to be congruent with 2 to the 3 times 2 to the 3 times 2 to the 3 times 2 to the 3 times, well, actually I can do 2 to the 4, right? So I can do 2 to the power 4, 2 to the power 4 times 2 to the power 2. It's going to be congruent with 16 times 16 times 4 mod 13. So I'm looking at this mod 13, right? Well, 2 to the, so 16 is going to be congruent with 3. So I can write this as like 3 times 3 times 4. So this is going to be congruent with 9 times 4, which is 36, which is going to be, well, 36 is going to be, so I guess this is going to be congruent with 30. So this is 36, right? So 36 is going to be 26 plus 10. Wait, sorry, 26, 30, yeah. So this is going to be just congruent with 10 mod 13. Okay, so cool. So yeah, so basically I got this is congruent with 10, and this is congruent with minus 3 mod 13. Yeah, so that's the case in here. How about 3 to the power 10? Well, if you look at 3 to the 10, 3 to the 10 is going to be congruent with, I guess, what can I do? I can do 3 to the power 3, right? So 3 to the 3, 3 to the 3, 3 to the 3 times the 3, which is going to be congruent with 27 times 27 times 27 times 3. You see why I use 27? Because 27 is congruent with 1 mod 13, right? So mod 13. So this is going to be congruent with 1 times 1 times 1 times 3, which is going to be congruent with 3 mod 13. Okay, so this is cool. So it turns out that this entire thing here, 2 to the 70 is going to be congruent with minus 3 plus 3, and it's going to be congruent with 0 mod 13. So what did I get? I got that this number is a multiple of 13. The remainder is going to be 0 in here. Okay, so hopefully this is clear how we use, a Fermat's theorem. It's just basically you're trying to find out, what powers give me 1, right? And for 13, you see that if you raise it to the 12th power, as long as a and 13 are a good pair, as long as a is not a multiple of 13, because 13 is a prime, as long as, they're good, a is not a multiple of 13, I can, get any number. 2 to the 12, 3 to the 12 would work. They would always be 1. So if I were to do that, then 2 to the 70 just becomes 2 to the 10. See? So that's kind of like the beauty of Fermat's theorem. You take a high power, and you can take any high power, and you can make it a small power here. Okay, so hopefully this is clear how this is going on. Okay, so this is nice. So now let's see, maybe we can do more with this idea. So let me clear this for now for a second. So if you guys drew, I can put this thing here in the chat. Yeah, I'm gonna share the link from Brilliant. So basically, yeah, this is how it works. You can read more stuff for here. Well, Fermat's little theorem is also good for primality testing, right? So like it can tell you very quickly if a number is a prime or not. Yeah, but this one is kind of like a slightly more advanced concept. So we'll skip this concept because it's a bit more advanced, and I don't think it's required at like the introductory level in Fermat's little theorem. Okay, so now let me go back to my whiteboard in here, and let's see what can we do next. Okay, so I guess we have Fermat's little theorem, right? And we got, a to the power p minus 1 is 1 mod p. So I guess if we're working with mod 5, I get that a to the power 4 is going to be congruent with, 1 mod 5. Okay, cool. So now the question is, can I do this theorem, but like more generally? So like, well, what if now I don't work mod p? What if now I just like work generally like, mod n, right? Can I do the same thing mod n? So the question is, can I, if I look at Fermat's little theorem, can I get something like a general Fermat theorem? So can I get something like along the lines of this? Can I get something a to the power n minus 1 is going to be congruent with 1 mod n for like some specific conditions? Can I do this? So can I do this? Yes or no? So turns out sometimes it could work, but most of the time this is not gonna work. Actually, like all the time it's not gonna work unless n is a prime. If n is a prime, it's gonna work. Otherwise, it's gonna be a trouble. Right? So how can I do this? Well, let's look at a couple examples. So similarly, I can construct the set Sn, right? So I can construct a set Sn, which are like the possible remainders of, mod n. So those would be, 0, 1, 2, 3, all the way until, n minus 1. And if I wanted to exclude 0, if I wanted to remove 0, I can make it Sn star, right? So if I make it Sn star, it's all the possible remainders, but without 0. Maybe a better notation, maybe I should have actually called this Rn because these are the possible remainders mod n, but well, I'm already using Sn, so it's fine. But yeah, so let's call this set Sn. Well, let's look at a couple examples. Let's look at some simple sets. So how about I work with the set S6, right? So if I were to look at the set S6, what do I have? Well, this is going to be 0, 1, 2, 3, 4, 5, 5, right? 6 is already remainder 0. Okay, so what if this becomes tricky? Let me see if I can. Well, yeah, so let's take this set as 6 and let's look at this in more detail. Well, if I take this set and let's say I multiply this set by 5. So let's say I look at the set 5 as 6. So if I were to look at this set 5 times as 6, well, what do I see? I see that I'm gonna get back the set 0, 5, right? 5, 10, 15, 20, 25, right? And now if I were to, simplify this, so if I were to simplify this, 5, the set as 6, this is actually going to be congruent with, well, 0. 5 is going to be congruent with 5. Well, what is 10 mod 6? So remember, we're working mod 6, right? So 10 mod 6 would be equal to 4. What about 15 mod 6? Well, this is 12 plus 3, so it's going to be 3. What about 20 mod 6? It's 18 plus 2, so it's going to be 2. What about 25? Well, it's 24 plus 1, so it's going to be 1 mod 6. So this is interesting. So turns out that, this remainders here and this remainders here, they're the exact same remainders. So it turns out that the set 5 times S6 is going to be congruent with the set S6. So this kind of like raises the question, well, is this always the case? If I multiply A by S6, is this always going to give me the set S6? Yes or no? And turns out that this one is good, but generally it's not going to work. Well, let's see why wouldn't it work. So I guess the reason this worked is because 5 and 6 were good numbers. So the reason it worked in here is 5 and 6 are, a good pair, but if it's a bad pair, it's not going to work. Let's see why 5 is special and why something else wouldn't work. So if I were to try another number, so maybe what would be another number to try? Well, if I tried let's say 2s6, right? So if I look at 2s6, well, what would I do? I just take all these numbers, double them. So I'd get 0, 2, 4, 6, 8, 10, right? Okay, so if I take these numbers, well, and now what is this gonna be? So if I take this number, so 2s6, and I will write them mod 6, right? Well, 0 is just gonna be 0, 2, 4. But what is 6 mod 6? Well, 6 mod 6 is 0. And what about 8? 8 is gonna be 2. And what about 10? Well, 10 is gonna be congruent with 4, right? Okay, so you guys see this is the problem. If you look at like all these remainders here and all these remainders here, like these two are not gonna be the same, right? So this one and this one, they're not gonna be the same. What is the problem? The problem is that numbers keep repeating. So because 2 and 6 are a bad pair, 2 and 6 are congruent with 2. This is bad pair. what's happening is that I'm getting multiple zeros. So when I take 2 and I multiply it by, by 3, for example, this gives me an extra 0, right? So if I have 2 zeros, that's already clear that this cannot be the case. So basically, I cannot have more than 1 0. If I get like any other zeros in here, then that's a problem. And here I multiply 2 by 3, it gives me a 0. So why does 2 times 3 give me a 0? Well, because 2 is a divisor of 6. 2 and 6 have something in common. So 2 and 6 are bad numbers. So if you were to multiply a, so if I take any a and I multiply it by S6, then I'm going to get the remainders 0a, 2a, 3a, 4a, 5a. As long as a and 6 are good, so if a comma 6 are good. So basically, if they're equal to 1, So basically, if I had a good pair. So it turns out if a and 6 are a good pair, this is always going to be the case. These two are going to be equal. So basically, the remainders in here. So let me make this slightly nicer. So the remainders here and the remainders here, they're going to be the same. Same only if, a and 6 are a good pair. But if they're not a good pair, if a and 6 are, like not equal to 1, so this is, if they're a bad pair, if I had a bad pair, then this cannot be equal, not same. These are going to be bad, not the same. Does this make sense, guys? So let's maybe try and prove this, because you clearly see in this example, look, 5 and 6 are good. So when I multiply everything by 5, I get like stuff good. But if I multiplied everything by 2, 2 and 6 are bad. So I got some like extra zeros in here. So let's try and prove this more like generally, this idea with like the set as n. So if I had a set as n, right? Okay, so why do we need a to be a good number? So you'll see in one moment. So let's look at this set as n, right? So the set of possible remainders mod n. So I have 0, 1, 2, 3, 4, all the way until n minus 1. Well, if I take a number that's good to n, so if a and n are good, so if a comma n are good, and if I look at the number a as n, well, what do I get? I'm gonna get 0, 0, a, 2a, 3a, 4a, n minus 1a. So can I show that these two sets are the same? Yes or no? Well, let's see. So if a and n are good numbers, let's say that I had, well, we'll look at this. Well, this 0 with this 0 is the same. So I can just like remove the zeros. So maybe I just get rid of the zero. So maybe I look at this with star and this with star. So I just get rid of zeros. The question is, can I show that this remainders here are all the same as this remainders here? Well, I have here all the possible non-zero remainders, right? All the possible remainders that are not zero. So there's n minus 1 of them. And in here, I have n minus 1 remainders. So if I show that they're all different and they're not zero, so basically, as long as they're not zero and they're all different, they have to be all these remainders, right? Actually, in the previous proof with Fermat's little theorem, I missed a little detail. I also needed to show that they're not zero. They're not zero in here. So like none of them. So I need to show that they're all different. They have same size, but none of them is zero. You can easily see that none of them is zero. Why is none of them zero here? Because, well, if I had ka congruent with 0, right, mod p, it would mean that p would divide ka. P would divide ka. But clearly p cannot divide. Look, p doesn't divide any k, p doesn't divide any a, so p doesn't divide any ka. So basically, it means that ka cannot be equal 0 mod p. Right? Specifically because a and p are good, right? Because a and p. So all of these are like non-zero. Show all remainders are different. And maybe I should add also non-zero. So they're all different and different from 0. They're all different and non-zero. So maybe I should say it like this, and non-zero. So if all the remainders are different and non-zero, they have to be all these possible remainders, right? Same story basically happens in here. Look, you have n minus 1 remainders and they're non-zero. So if I show that these are all different, they're not zero, they have to be exactly these possible remainders. Well, how can I show that they're not zero? Well, can I have any of this? Can I have some, ka in here that's, congruent with 0? Well, what if ka was congruent with 0? So if ka is going to be congruent with 0 mod n, well, what do I have in here? Well, it means that n needs to divide ka, right? But look at this. A and n are good. So because a and n are good, I can cancel the a. So from here, I'm going to get that, n needs to divide k. And this is not possible. Not possible. So I cannot have any number here to be 0. Now I need to show that they're all same size. So the sets have same size clearly. So the size of, so I can also write this here. So Sn as the size of, Sn star is going to be the same as the size of ASN star. So the sizes are going to be n minus 1. So we have same size. So now I need to show that they're all different. So the last thing that's left is to show that they're all different. How can I show that they're all different? Well, suppose there's two of them that are the same, right? So what if I had two numbers that are the same here? So what if I had, some Ka and some Sa later on? And let's say that they're both the same. So if I had some, Ka, so now this is another idea. So if Ka was congruent with some Sa mod n. Well, look at this. Because A and N are good, right? A and N are good. I can come and I can cancel the A on both sides. And what would I get? I would get that, from here, it means that K needs to be congruent with S mod n. But this is not possible because K and S are numbers between 0 and 1, right? So basically, K and S, K comma S, they're greater than, 0 and less or equal than n minus 1. So greater or equal than 1. So the only way this can happen is if K is equal to S, right? So this is basically the conclusion. So otherwise this cannot happen. So basically it means that all the remainders are different. So from here, all the remainders are different. So it results that, so from here I'm going to get all remainders are different and not equal to 0, right? So all remainders are different. They're not equal to 0, and there is n minus 1 of them. So they have to be the same set. So from here, from all of this stuff, so basically from all of this, it results what? It results that this has to be the same set. So basically the set Sn has to be the same as the set ASN. So it turns out that this is true, but if and only if, only if only if A and N are good, right? So A and N have to be a good pair. Where do I use good pair? So the good pair, this idea of like good pair, it's used in here where I do the simplification, and it's also used in here. So I use this idea of like A and N being good in two cases, here and here. Otherwise, if A and N wouldn't be good, I wouldn't be able to do this. Okay, so this works. Okay, so I have A and N is good. So okay, so the question is, can I still do the same stuff? So basically, I'm gonna pick some set Sn. So the question is, if I were to pick, A to be a good number, right? And then instead of looking at P, I look at the set N, right? So if I look at like Sn here, if I do this to be my Sn, and if I do this to be my ASN, which is gonna be n minus 1, right? So basically instead of like P, I use Sn. So, if you look at like this, what was this initially? This was, your SP. Maybe I should, so if I complement this was your set SP, I guess started without a 0, and this was my set ASP, also, with a star because it doesn't contain 0. Okay, so the question is, if I come and I replace this with n, 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 the question is, can I still do the same thing? Can I replace this with n? Can I replace this with n? Can I replace this with n? This with n, this with n? So the question is, if A and N, so if A and N was a good pair, can I do this thing? Turns out, no, there's going to be a problem with this simplification here, right? Because, well, what do you see? This is going to be mod n, right? So now I cannot simplify 2 on both sides. I can only simplify 2 on both sides if 2 is good to n. But if 2 is bad to n, it wouldn't work. So let's write basically the same stuff again. So yeah, if I were to rewrite the same stuff again, so what did I get? I got that this set Sn is the same as the set ASN, right? So these two sets are the same. So what's happening if I were to, basically the question is, well, if I multiply all the numbers in here and all the numbers in here, I should get back the same thing, right? So if I were to look at, the set Sn, so if I look at the set Sn, star, because I don't want to use the 0, so I use, 1, 2, 3, 4, all the way until, n minus 1. This should be the same as the set, ASN, which is, A, 2A. So set A, 2A, 3A, 4A, all the way until n minus 1A, which is basically the set ASN, right? So it's the set Sn that's multiplied by ASN star because it doesn't contain a 0. Okay, so well, these two sets are the same. We just proved it in here. As long as A and N are good. If A and N are good, this works, right? So I should make a note somewhere here that A comma N have to be good pair. So good pair. Otherwise, this doesn't work. So it only works if it's a good pair. Well, so I guess if I have this thing, the question is, what's happening if I multiply everything on the left and everything on the side, on the right? Okay, so if I were to take and I multiply everything on the left, what would I get? So I'd get 1 times 2 times 3 times 4 times 5 times n minus 1. This would need to be congruent with, well, what's the product in here? Each one of them has an A, so how many A's? There is going to be a to the power n minus 1 times a 1 times a 2 times a 3 times a 4 times a 5 all the way until n minus 1 mod n. Well, but now look at this. If n is not a prime, right? If n is not a prime, then n is going to be made out of two numbers, a product of at least two numbers, a and b, right? So somewhere here I'm going to have an a, or sorry, n is going to be a product of like some numbers, x times y, right? So somewhere here I'm going to have an x, somewhere here there's going to be a y, so somewhere here is going to be an x, somewhere here is going to be a y. So the thing is I cannot common simplify, right? Because look, x and n are bad, right? So n x is a bad pair. It's equal to x. It's a bad pair. I cannot common simplify the x. I can only simplify on both sides if they're good numbers, right? If you remember the simplification trick, when can I simplify on both sides? I can simplify on both sides the same number if n and t are good numbers, right? But in here, you see, because so when I looked at prime numbers, all of this were good to p, right? All these numbers, they're good to p. The only number that is bad to p is going to be p itself. But if n is a composite number, it has many bad numbers, right? N is going to have many bad numbers. So for example, if n was equal to 12, if I were to look at all these numbers between 1 and 12, so if I were to look at all these numbers between 1 and 12, so 1 2 3 4 5 6 7 8 9 10 11 12, you see that there's a bunch of bad numbers. What are going to be? So this is bad, 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 this is sorry, I shouldn't use 12 because it starts from 0, right? So it's going to start from I should also write 0 here. So 0 is also bad to 12, right? So 0 is also bad. So actually, if you look at like, okay, between 0 and 11, right? So I look at like the set as 12. So I look at the set, as 12. Well, this is all the possible remainders between 0 and 11. Well, what do you see, guys? You see that there's a lot of like bad numbers. All the numbers that are cut are bad. So the only good numbers, so I can create another set, good 12. So what is going to be good 12? These are going to be the good remainders. What are the good remainders? The good remainders are going to be 1, 5, 7, and 11. So 1, 5, 7, and 11 are the only, good remainders. So these are like good remainders, good remainders, mod 12. So this is, I call this set G12. G12 because these are like the good remainders mod 12. So what do I see in here? You see that there's like a lot of like bad numbers. So if I were to do this thing with 12, I wouldn't be able. So if I cancel x and y, so let's say that in this case, let's say that n was, in my case, n was 12, right? So n was 12 in here. If n was 12, clearly 2 and 2 is a problem. I cannot cancel 2 on both sides because 2 and 12 is a bad pair, right? 3 is also bad. If you look at like 3 and 3, I can also not simplify 3 on both sides because 3 is also bad. The only thing that I can simplify is the good number. So for example, I could simplify the 5. I could simplify the 5 on both sides because 5 is good to 12. 7 is also good, so I can keep going, and then 7 in here, and I keep going, is going to be a 7 in here, so I can cancel the 7 and a 7, and then I can cancel, the 11 and the 11, and yeah, so these are basically the only numbers that I can cancel. So basically, if I wanted to do this cancellation, I cannot do cancellation, right? Can't cancel for bad numbers, so I should specify it here. So here and here, can't cancel the bad numbers, right? Bad remainders. The bad remainders. So well, what should I do in that case if I have bad remainders? So, well, if I have bad remainders, why don't I just like leave out all the bad remainders? So basically, if I look at like S12, well, there's gonna be some good remainders and some bad remainders. So the bad remainders cannot be canceled. So why don't I just keep the set of good remainders? So, how about I just look at the set of like good remainders of 12? So instead of like working with the set S12, how about I work with the set G12? So basically, G12, these are going to be the good remainders of 12, right? So these are going to be what? 1, 5, 7, and 11. So these are the good remainders. So now here is the question. Well, if I take any number a that's good to 12, so if I take, some number a and 12 that's a good, so if I take, yeah, let's do something like this. So I'm going to take, a and 12 to be a good pair. So is equal to 1. So, well, what is going to happen if now I look at the set a times, G12? So for example, if I pick a good remainder, 5 times 12, right? So 5 times, G12. Well, what's going to be this? It's going to be, 5, 25, I gave 35, right? And then 55, right? So these are going to be all the possible remainders, when I look, at 5 times G12, right? Well, but now if I were to, simplify this and write this mod 12, so if I look at, 5 times, G12, this is going to be congruent with, well, 5 is still going to be 5. Well, what is 25? 25 is going to be 24 plus 1. So this is going to be congruent with 1. Well, what about 35? Well, 35 is going to be, well, what's going to be that? It's going to be 36 minus 1, right? So it's actually going to be congruent with minus 1. So it's actually going to be congruent with, so if you look at 35, 35 is going to be what? 24 plus 11. 35 is 24 plus 11, so it has a remainder 11. So what about 55? Well, 55 is going to be, I guess, 48 plus 7, right? So 48 plus 7, 48 is a multiple of 12, so I'm going to have remainder 7. So what did I get? So basically, I get this property that if, I take only the good remainders mod 12, and I multiply by any good number. So for example, 5 is a good number. Then basically, I also get back the same set. So here is another property. Basically, if you take some good set Gn, so if you take some good set Gn, some good remainders Gn, and you multiply it by some number a that's also good to n, then you're gonna get back the same set Gn. So basically, these two sets are the same set. So the same idea that happened, this case also happened, for generally for like Sn, for like any Sn. So any Sn, but you wanted a and n to be good. But then in here, if I look at only Gn and same sets are same sets. But I also need a and to be a and n to be relatively prime. So basically, I also need a comma n to be 1, a good pair. So good pair. So as long as I have the good pair, I can, as long as these are like a good pair, I can, get this thing that AGN is going to be the same as the set GN. Okay, so let's see how could we do this. Well, so if I take a GN, so if I look at GN, so let's write down all the good remainders mod n. So I'm looking at good remainders mod n. So let's say that Gn was equal to some, I don't know, like maybe R1, R2, R3, R4, all the way until Rk. So all the way until some Rk. So basically, these are like good remainders. So these are good remainders. There's mod n. So what does this mean? It means that R, Rk, R, if I take Ri and n, these are gonna be equal to 1. So right. So basically, I have good remainders. So if I take any R and n, so remainders mod n, so these are good remainders. So it means that if I look at like R comma n, these are equal to 1. So these are the good remainders, right? So this is my set Gn. So let me make it nicer. So this is the set Gn that contains the good remainders. Well, then what did I say? Well, now if I take a and n to be relatively prime, so if I take a to be a good number, and if I look at the set Agn, let's make G nicer. If I look at the set Agn, which is going to be AR1, AR2, AR3, all the way, so basically AR4, So let me write down. So AR4 all the way until like some ARK. Turns out that these two sets are going to be the same set. So if, as long as, you know, A and N are good. So if A and N, so we also need A and N to be good. So if A and N are good, so A and N are also, you know, good pair. Good pair. Then basically these two sets are going to be the same. So the set A GN is going to be the same as the set GN. So how can we show that? Well, first of all, let's assume that these remainders are literally in increasing order. So start with the smallest one. So actually you can tell right away that the first remainder is going to be 1, because 1 is going to be good to n, right? So what are the good remainders? The first one is 1, and n minus 1 is also good to n. Also, check one thing, that these two remainders, they go in pairs. So if, for example, if x and n are relatively prime, then, you know, n minus x, and n are also going to be relatively prime. So basically, you know, if this remainder here is going to be x, this remainder rk minus 1 is going to be n minus x. So all these remainders, they sort of like go in pairs. That's the thing to keep in mind. So if x and n are good, n minus x and n are also going to be good. So, you know, the good remainders, they always, you know, are complementary. So x is good to n. If x is good to n, then n minus x is also going to be good to n. Okay, so okay, but we don't know if this one is a 2 or a 3, or it depends on n. If n is even, then this one cannot be 2, right? If n is odd, then obviously 2 is going to be good. Yeah, but you know, these numbers can be whatever, as long as, you know, they are good to n. Okay, so how can we show that these two sets are the same? Well, first of all, notice they have same size. So basically the two sets, so I can write this down here, you know, gn and gn have same size, so have same size k, right? Which is equal to the number of good remainders, number of good remainders, right? Remainders mod n. So both of them have the same size, and then gn contains all the good remainders. So if I show that, you know, all of this are, so look, these are k remainders. So if I show that they're all different, and if I show that all these remainders are also good, then I'm basically done. So basically I need to show, so need to show AGN are all the good remainders. So this set AGN are all the good remainders. So now the question is, how can we show that these are, you know, all the good remainders in here? So what could we do? Well, first of all, we need to show that all these numbers are good, and we need to show that they're all different. Look, if all of these are good, and if all of them are different, and there's k of them, they have to be all the good remainders, because there's k good remainders, and if they're all good, and they're all different, and they're k in total, they have to be exactly all the k good remainders. So we need to show that all good remainders. So basically two things that are needed to show in here. So we need to show that they're all, you know, good. So first of all, how do I show that? Look at one thing. So first of all, I have that A is good. So A and N is good, and R and N is also good, right? So now remember this: if, you know, I picked R and N to be good, and A and N is good, then I can combine them. So if I combine them, I'm gonna get that AR and N is also, you know, good. So basically good pair. So what did we just get? We just got that all these numbers in here are good, because you take good numbers and you combine them with another good number A. So then you're gonna get that they're all gonna be good. Actually, yeah. So okay, so all of these numbers in here, they're gonna be good, right? And how do we know that this is the case? Well, because we just used this theorem that we actually proved a while ago in the beginning, where we had, you know, if I had A, B, and N is relatively, you know, A, B is good to N, it means A is good to N and B is good to N. And the other way it also goes, if both A and B are good to N, then it means that AB is going to be good to N, right? So if I were to go all the way back to my property in here, look, A is good to N, R is good to N, it means that AR is good to N. So all of these are like good numbers. So all of them are good numbers. So basically I need to show that they're all good remainders. And I need to show that they're all the good remainders. So basically I need to also show also different. So that I also need to show also all different, right? So different. So how can I show that they're all different? Well, again, you know, let's assume that there's two of them that are the same. So maybe there is, you know, some ARS is going to be the same as like ART in here, right? Well, then what's the problem in that? Well, if I were to have this, then, if I were to take this two and put them somewhere here, I'd have, if I had some ARS, is going to be congruent with some ART mod n. First of all, notice one thing. A is good to n. So because A is good to n, I can cancel the A. So what would I get? I would get that RS is going to be congruent with RT. So RS is going to be congruent with RT mod n. Well, what's the problem in here? The problem is that RS and RT are going to be numbers that are less than n minus 1 and strictly greater or equal than 1. So this cannot happen. The only way this can happen is if RS is equal to RT. So this basically means that RS needs to be equal to RT, right? So basically they're all different in here. So if I pick two remainders, if I pick some RS in here and some RT in here that are different, then I cannot have this. This cannot happen. Right? So this thing in here cannot happen because I'd get a contradiction. Like the only thing, the way this can happen is if RS is equal to RT. So if I start with RS not being equal to RT, I cannot get this, because if I had this would mean this. I simplify the A's and I get this, and it means that RS has to be equal to RT because they're both between. So this basically, what I'm trying to say is that if RS is equal to RT, if RS is not equal to RT, if the two of them are different, right? If the two are different, then this cannot happen in here. Can't happen, right? So can't happen. So they all need to be different. All different, right? Different. Okay, so now look, all these remainders are good. They're all different. There is k of them, right? So if there's k of them, then it means that it needs to be all the good remainders. So from here follows the conclusion, right? So the main conclusion is that that this set AGN needs to be the same as the set GN. So let me put this in here. So if and only if A and N are good pair, A and N are good pair, right? Good equal 1, which means good pair. Okay, so this is nice. So basically, now that we know that these are good pairs, what can I do with these two sets? If these two sets are the same, I can multiply them, right? And keep in mind, these are all good remainders, so all of them can be simplified. So now if I were to write down, the set GN, so if I write down again GN, the good remainders, maybe GN star, because actually, so if I write down the good remainders, so let me do this again. So GN, which is the good remainder, so it's going to be R1, R2, R3, all the way until some RK. And well, what did I get? I got that this is the same as the set AR1, AR2, AR3, all the way until ARK, which is the set AGN, which is A times the good remainders. Well, I got that these two sets are the same set, so they're congruent, right? So, well, I can multiply all the stuff on the left with all the stuff on the right. Sorry, so all this stuff. So basically, if these numbers are congruent with these numbers, then this product is going to be congruent with this product, right? So I would have what? I would have R1 times R2 times R3 times RK is going to be congruent with, AR1 times, AR2 times ARK. But well, how many A's am I going to have in here? I'm going to have K A's. So basically, this is going to become, A to the power K, and then, R1 times R2 times R3. R3 times all the way until RK mod n. And now here is the beauty. Look at this, because R1, so basically each R and N are good, right? So Ri and N are a good pair because, this is the set Gn, it contains only the good remainders. So if Ri and N is a good pair, it means that I can simplify R on both sides. R1 can be simplified. R2 is good to N, so I can cancel R2. Now R3 is also good to N, so I can also cancel R3. Now RK is also good to N, so I can also cancel RK, right? Because they're all good numbers. I can cancel all of them and all of them because, look, actually I can go the other way. I know that, R1, R2, R3, Rn are good, so their product is also going to be good. So the entire product can be canceled, and the entire product can be canceled on both sides because this is going to be a good product, and this is going to be, well, all these numbers are good. Their product is going to be good to N. So this is good to N. This is good to N. So I can cancel both of them. So what am I going to be left with? I'm going to be left with this property that 1 is going to be congruent with A to the K mod N. So now this is called Fermat's little theorem. So basically, you get that A to the power of, so you get A to the number of, good remainders. This is going to be congruent with 1 mod N, right? And now there is a special function, which is called phi of n, which is Euler's function. And that one is actually equal to this number. So this thing in here, the number of good remainders, this is called phi of n. So basically, this is Euler's function, which says that, phi of n is equal to the number of good remainders, which is also equal to k. So basically, it's equal to, so this number phi of n is equal to k, is equal to the number of good remainders, which is equal to the size of this set Gn. So the size of this set is equal to k, which is the number of good remainders, which is called phi of n. So phi of n is basically the size of this set. And there is a formula for like every n, there is a formula that tells you how you can figure out what this k is, what's the size of this good remainders. And we'll see. If we have time, maybe we'll discuss it. If not, we're going to be looking at this in the next class. But basically, this is a very, very cool, very, very interesting property, right? All right, cool. So this phi of n is a number of good remainders, mod n. Okay, so yeah, and then you basically get your formula that a to the phi of n is gonna be congruent with 1 mod n. Well, actually, here, one more more extension that I wanted to add. It's kind of like very simple idea, but look at this. This thing works for 2 of them, but it also works for 3 of them. For example, if I had, let's say that, I had that a and n is good, and I had b and n is also good, and I had that c and n is also good, then one thing I can do is I can combine all 3 of them, and I can also get a, b, c, and n is also going to be good by the same idea, because, the way I can do it is I can basically, for example, combine 2 of them, and I'm going to get a, b, and n is good. And then I also have, C and N is good. And then look, I can combine this two, and I can get A, B, C, and N is also going to be good. So basically, if you had 3 of them, you can combine them and you get all 3 of them are good. And it can also go the other way. Look, you can also go the other way, right? So basically, if you had that 3 of them are good, you get that all 3 of them, the product is also good. And if the product is good, that all the components are good. So actually, you can keep going like all the way down. So let's say that I also had x and n is good. Then, well, if you can combine all of them, if you can combine, all of these terms together, you're gonna get also that a, b, c, d, x, and n is also gonna be good, right? So basically, if you have a bunch of good numbers to n, their product is also going to be good to n. And if the product is good to n, then you can go the other way and you can say that, all of these numbers are also going to be good to n. Yeah, and then basically, well, why is that helpful? Because in this formula in here, look at this. All these remainders are good to n. So if I were to, take this thing, this product, and call this r, and call this r, right? Then, well, because all these little r's are good to n, all these little r's are good to n, their product is going to be good to n. So basically, I'm going to get a formula that looks like this. R is going to be congruent with r times ak, right? Or ak. So basically, r is going to be congruent with r times this. And look, r, so from here, I'm going to get that big r, and n is also going to be good. And I can cancel r on both sides, right? I mean, you can either cancel the entire product, which is what I just did, or you can cancel them one by one. Either way works, but yeah, both of this r and r are good. So that's why you can cancel r and r on both sides. So you're just left with, this formula 1 and ak is good. So from here, you're going to get that, r and n is also good. Okay, cool. Yeah, so now I guess maybe we can do some practice problems. So this is called Euler's theorem. So maybe I should write the name. A to the phi of n. So yeah, let's write down the name. So this is called Euler's theorem. Here is actually a question, guys. What is gonna be phi of p? This is basically, number of good remainders, remainders in GP, right? Well, but what are the good remainders in GP? Well, this set GP is going to be all the good remainders between. So when I say here good remainders, it's actually good remainders between 1 and n. So I should say between 1 and n, right? So I look at the set between 1 and n, and I say, okay, what are the good remainders in this set, right? So here is the good remainders in GP between 1 and p. So it's going to be the numbers between, 1 and, p. So what's going to be? Well, p is not going to be good. So it's going to go all the way until p minus 1, right? So all the good remainders are going to be between 1 and p minus 1. So this is actually going to be p minus 1, which is going to be, so GP is actually the same as SP, right? Because basically all the numbers between 1 and p minus 1. So they're all going to be, so okay, so actually there's a cool problem. So phi of p is equal to p minus 1. So actually, Fermat's theorem is a special case of Euler. So if I replace this with p, and if I replace this with p, then this thing becomes equal to p minus 1, right? Phi of p, look, phi of p is equal to p minus 1. So a to the power p minus 1 is going to be congruent with 1 mod p. So yeah, so Fermat's theorem is basically a special case of Euler's theorem. Now, if you want to read more about Euler's theorem, maybe I can share some links with you. So let me take a look if I have anything useful. Euler's torsion function. Give me 1 second. Yeah, so I guess if you want to read more about Euler's theorem, so let me share my screen. So again, Brilliant has some like great resources. So I'm gonna put, this here in a chat. So you can, if you access this link from Brilliant on Euler's theorem, it's also like really useful. So basically, it's basically saying that if you take a to the number of good remainders, k, which is, phi of n defining here, this is always gonna be congruent with 1 mod n. What is this phi of n? This is the Euler torsion function. This number is a counter. It counts how many good numbers you have. So basically, you take all the numbers between 1 and n, right? So you take all the numbers between, so you take the numbers between 1, 2, 3, all the way until n, and you check only the good numbers. So from here, you only pick good numbers, pick good numbers, or good remainders. So I should say good remainders mod n. So good remainders mod n. So there's going to be k of them. So R1 all the way until Rk. So these are going to be the good remainders. So k in total, k, which is equal to phi of n in total. So basically, this one is a counter function. Counter function, because this function basically counts all the good remainders mod n. So you look mod n, and you're like, okay, which one of them are good, right? So you're going to get them. Yeah, so I guess if you look in here, you can look at a couple different examples. Maybe it's worth for me to just like, use a whiteboard in here. So for example, okay, this simple property, we can probably clear this. So let's look at like some simple examples for phi of n. So for example, what's going to be phi of 6? So if I look at the good remainders, like 1, 2, 3, 4, 5. So if I look at like stuff mod 6, right? So mod 6. So mod 6. So what are going to be good remainders? So what numbers are good mod 6? Well, 0 is bad, 2 is bad, 3 is bad, 4 is bad. So actually for 6, we see that G6, the good remainders mod 6 is just going to be 1 and 5. So, right? So then basically, I guess phi of 6, which is going to be equal to the size of the set G6, is going to be equal to 2, right? Only two numbers, 1 and 5. Well, what about, for example, G10, right? So mod 10. So if I were to look at this numbers mod 10, so if I pick the numbers, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, I look at this numbers mod 10. What are going to be the good remainders mod 10? Look, 0 always, I can actually not even write 0, because 0 is always going to be a bad remainder. But like, well, 10 is made out of 2 and 5s. So everything that has a 2 and a 5 has to disappear. So 2, 4, 6, 8, they're all going to be bad because they're even, and 10 has a 2, so 10 is also even. And then also 5 is going to be bad. So actually, if I look at, G10, so this was S10, right? So S10 is all the remainders. So if I look at just G10, which is just the good remainders, I see 1, I see 3, I see 7, and I see 9. So these are going to be basically all the good remainders. And, I guess if I wanted to get phi of 10, this is going to be the size of G10. The size of G10, which is equal to 4. So there's only 4 numbers for G10, right? Now the question is, is there like a formula? And turns out, yes, there is a formula. So if for example, n is equal, so if n is equal to, prime factorization P1, P2, pk to the power alpha 1, alpha 2, alpha k. So let's say that n is made out of these prime factors. Then if you wanted to get phi of n, so if you wanted to compute, phi of n and figure out, how many good numbers are there for n, which is the size of, gn, then this is basically going to be equal to n times, 1 minus 1. So basically 1 minus 1 over p1, 1 minus 1 over p2, all the way until 1 minus 1 over pn. So yeah, so basically this is the formula for phi of n. Actually, another way to rewrite this formula, a slightly better way to rewrite it, is basically rewrite it like this, like p1 minus 1 divided by p1 times p2 minus 1 divided by p2 times all the way until pk minus 1 divided by pk. So this is the formula for phi of n. And the way you can think about this formula, this is basically a probability, because if you ask, okay, if you picked a number, let's say, well, I guess I'm gonna cancel some of the stuff. So let's say that I had some numbers, let's say that n, okay, so I have this set, gn, which is the good remainder. So r1, r2, all the way until, rk, that are good to n, mod n. So mod n, right? So these are good remainders. So basically it means that r, ri, and n, Ri and n are, good remainders. Well, then what does this mean? Basically, if you think about this, well, look at n. So if you think about r, well, r and n are relatively prime. So n and r are a good pair. So you can start it like this. You can say that, n and r are a good pair. But what is n? Well, n is made out of prime numbers. So n, you can decompose n into like p1 alpha 1 times p2 alpha 2 times, pk alpha k. And r, right? So these are, good numbers, r. So these are, good numbers. Okay, so what does this mean? Now think about the theorem here where I had a, b, c, d, and r. These are equal to 1. Well, if the product is good to r, so basically if all a, b, c, d, and so on are good to r, it means that each one of them individually needs to be good to r, right? So basically what we just said in this theorem in here, well, if I have, a bunch of numbers that are good to, let's say, r, now instead of n, I use r, then the product needs to be good to r, right? So basically, if the product is good to this number, it means that all the numbers individually, they need to be good to this number. So basically, same story in here. If all of these pi's are good, the entire product is good to r, it means that each pi individually needs to be good to r. So basically, you need to get that, like, p1 to the alpha 1, and r needs to be good, p2 to the alpha 1, alpha 2, and r needs to be good. And then basically you can keep going all the way until, pk to the alpha k and r, they also need to be good, right? But, well, what does it mean for p1 to the alpha 1? Well, the power doesn't matter. If p is relatively prime to r, p to any power is also relatively prime to r. So basically what this means, it means that p1 and r need to be good, p2 and r need to be good, all the way until, pk and r need to be good. So basically a number in here, like some number, is going to be good to n only if this number r, so this r in here is going to be good to n only if this r is good to all the primes in n, right? So basically r is good to n if and only if r is good to all the primes that are inside of, inside of n. Well, and now what is the probability that r is good to p1? So if you think about all the numbers that go from 1 to n, so if I write down all the numbers, let's write them down like this. So I have the numbers, 1, 2, 3, all the way until, p minus 1, and then p, and then p plus 1, and then 2p, and then and then 3p, and then 4p, all the way until, n. Then what do you see? Well, actually, what's the probability that r is good to some prime number? So what's the probability that r and p are good? So r comma p are good. If I pick a number at random between 1 and n, what's the probability that is good? Well, if you look in this set all the way until p, so this here is p minus 1. Well, then what do you see? You see that all of them are good. So this chunk in here is going to be p minus 1 of them are good, p minus 1 good. And then you see one bad, right? So the probability, so basically in every group of p of them, same story is going to happen in here between p plus 1 and 2p. P minus 1 are going to be good. and 1 bad. Well, what are going to be the bad numbers? The bad numbers are going to be basically P, 2P, 3P, 4P, all the way until the last one, right? So basically, like every P number, so you do P and then skip another P and then another P, another P. All of these are multiples of P, so they're bad numbers. But everything that's in between, they're going to be good numbers. So basically, P minus 1 are good, 1 is bad. So the probability that a number is bad in each group has a probability of 1 over P that the number is bad. So 1 over P, probability that it's bad. Again, here also like 1 over P, probability it's bad. Here also, 1 over P, probability is bad. So these are the probabilities it's bad. Like I pick a random number and it's bad. What's the probability that I pick a random number and it's good? Well, the probability that I pick a random number that it's good, it's going to be 1 minus. So if I pick a random number from here, probability that it's good is going to be 1 minus probability that it's bad. Probability that it's bad. So this is equal to probability that it's good, right? So probability that I picked a good number. So probability that it's good is going to be 1 minus probability is bad. It's going to be 1 minus 1 over P, right? So this is the probability that is bad in here, probability that is bad in here. So same probability is going to be in here. Same probability is going to be in here, and such and such and such. So basically the probability that the number is good is going to be 1 minus 1 over P1. So this is the probability that is good here. 1 minus 1 over P2 is probability that is good here. And then 1 minus 1 over Pk is probability that it's good to K. Well, and if these are the probabilities that R is good to all of this, well, what's the probability that R is good to all of them? Well, it's going to be 1 times this, 1 times like this times this times this times this. So basically this, if you look in here, if you look at this formula here, this is probability. These are basically probabilities. Probability, good for P1. Probability, good for P2. R and P2 are good. R and P1 are good. All the way until, probability that good between R and Pk. So if you look at like all of this, which is exactly all of this, this is just the probability R and N are good. R comma N good. So, well, if I multiply this probability by N, so if you look at this thing, this is N times the probability R and N is good, right? So this is actually going to give you the number of like all good numbers. Now, I guess this is not quite a proof because, well, I didn't really go into like all the details in here. We kind of like skipped a bunch of details, but this is kind of like a good intuition how to think about this function phi of N. Phi of N is basically, it's telling you how many good numbers there are. Well, the number of good numbers, if I had 100 numbers and I ask you how many of them are good, well, it's going to be 100 times the probability that any number is good, right? The probability that the number is good is this times, how many numbers I have. So on average, you get this many good numbers. And turns out that this is the exact formula. And in future classes, we can, look at like the details of this computation. There's like other ways to also prove the same property. Okay, so hopefully you see the beauty of like why we care about good numbers, because good numbers are easy to simplify, right? Like if I looked in here, it's very easy to simplify all the good numbers. So yeah, we want to figure out, like we want to be able to compute this number K, the number of good remainders, very easily. And this function phi of N, it gives us a formula, and then we just saw what that formula is. All right, cool. So this is kind of like a good, I guess, stopping point on Fermat and Euler's theorem. I guess to review what were some of the main ideas from this class. Well, some of the main results were the simplification trick, right? So when can I simplify and when I cannot simplify? And I can simplify, it relies on this idea that T and N need to be good, right? So, T comma N, they need to be, good pair. So good pair. So if T and N are a good pair, I can do this simplification, right? So then I can, cancel on both sides. Okay, so now let's see here. Yeah, we saw when I can cancel them, right? So, if they're a bad pair, I can always remove out the bad pair, right? So when I remove out the bad pair, yeah, I can do the simplification. And then basically, what did I want to do? So one motivation was to figure out when does a high power give me remainder 1, because I can do a bunch of simplifications. And the solution to that was Euler and Fermat's theorem. But before getting Euler and Fermat, we kind of like investigated, right? So like here, Euler and Fermat's theorem. So Fermat is just a special case of Euler, because phi of P is equal to P minus 1. because before like showing that this is the case. And the proof is actually very simple if you build a lot of like understanding about the problem, is that you have to look at the special sets Sn. So I think the more important part of this class is actually understanding the sets Sn and understanding how they operate and how can you like switch from one set to another set. And basically noticing this idea that if you take any set, if it's prime numbers, right? It doesn't have to be prime numbers, can be any number n. So if you take it and if you multiply it by any good number, if 2, 3 in this case are good numbers, you get back the same set, is just shuffled around. So you can multiply it by any number a, you get back the same set shuffled around, as long as a and 7 or a and n are good. So I guess in our case, how did we show that? We showed that these two sets are the same because, well, they have the same size, and there's p elements in here, there's p elements in here, and then if they're if I remove the 0, if I show that all of these are different remainders and there's p minus 1 of them, they have to be exactly all of this. If they're all different and non-zero, well, clearly they're non-zero, because if p doesn't divide ka, well, if p doesn't divide a, p doesn't divide any k from here, p cannot divide ka, so ka cannot be 0 mod p. And also, if two of them were to be equal, what would be the problem? I can cancel a on both sides, and I'd get that k and s have to be the same number, because s and k are between 0 and p minus 1. There is no way this can happen, not possible, right? So all have to be different. If none of them is 0 and they have same size, they have to be all the possible remainders. So the same idea that we did for p, the same idea worked for n, right? But for n, we noticed that, well, again, I need to multiply by good numbers. If I multiply by a bad number, this is going to break down. The sets are not going to be equal. But if I multiply by good numbers, as long as I multiply, the set Sn and then ASN, I get the same. I get the two sets are the same. What is the proof? The proof is literally the same proof we had with Fermat, right? Like, you show that none of them is a 0 in here. And we also show that none of them, so I cannot have any zeros in here, right? Because why? Because n cannot divide Ka, n cannot divide, and n doesn't divide k, so n cannot divide k, right? So this cannot happen. So this n doesn't divide ka, so then basically this cannot happen, right? So basically this cannot happen. You cannot have any 0. They have the same size and all of them are different. Why are they different? Because you can write them like this and you can cancel a on both sides, right? So they cannot be equal. So they cannot be equal. So then basically you're gonna get that this set here and this set here are the same set. Okay, so now in Fermat it was kind of easy because you can just if I know that these two sets are the same, the Fermat has just one proof. You just write this product and this product, knowing that these two sets are the same, knowing that SP and ASP are the same set. If I just write the products and I simplify them, I get that a to the p minus 1 is congruent with 1 mod p, which is Fermat's little theorem. But then the question is, what if I try to do that generally for Sn? Can I do this? Turns out that no, this doesn't quite work. Why? Because I cannot do the simplification, right? For Sn, even if these two sets are the same, if I try to multiply all the numbers here and all the numbers here, I'd still, well, clearly I'd get that these two are the same, but this is all gonna be congruent with 0, and this is all gonna be congruent with 0. And I cannot, 0 is congruent with 0, that doesn't give me anything, right? If I try to simplify stuff, I cannot cancel terms because n in here, it can have, there's gonna be a bunch of bad numbers in here. All the bad numbers cannot be simplified. That's why, for like S12, what were the bad numbers? 0, 1, 0, 2, 3, 4, 6, 8, 9, 10. A lot of them are bad numbers. The good remainders, there are very few of them. G12. Here, this is the good remainders mod 12. So I said, okay, how about I just get rid of all the bad numbers and keep only the good numbers, right? Then I noticed that for the good numbers, I have the same property. As long as I multiply G12 by Gn, like the good remainders mod n, by some number A, some good number, a good number to n, then I also get back the same set of good remainders. And what was the proof? Again, same proof. I show that these sets are the same. How do I show? Well, they're all different. All different. Why are they all different? Well, because if I had two of them that are the same, I'll get that RS and RT has to be the same because A can get cancelled, right? So if they're all different, now how do I show that they're all good remainders? Well, all the R's are good. A is good. So if I combine A with R, I'm also going to get a good remainder. So all of these are good remainders. They're all different, and there's k in total. Well, there's at most k good remainders, right? That's what we know. There are k good remainders are 1 for Rk. So they all need to be the same. So these are all the same. And now it works. If I were to multiply them, all the numbers in here and all the numbers in here, I can simplify this product here with this product because these are good products to n. So when I simplify them, I get a to the k is congruent with 1 mod n. What is k? K is the number of good remainders, which is defined by this function phi of n. Phi of n tells me how many good remainders we have. And we saw it in here, right? So if we look at Here we saw a formula for phi of n, which is basically n times the probabilities that r is good for each of the prime numbers in n. Why do we need the probability that it's good for each one of them? Well, because of this property. If r is good to n, then r needs to be good to this. So r needs to be good to every, prime, like every component of n. So every r needs to be good to every p to like its corresponding power. But if it's good to p to some power, it also needs to be good to p. So what's the probability that r is good to like all of these p's? It's gonna be, well, the probability that is bad is 1 over p, because only like every p number is gonna be bad. So 1 over p of them are gonna be bad in here. But the remainder 1 minus 1 over p, these are going to be the proportion of good numbers. So the proportion of goods is this. Proportion of goods here is also this. Proportion of goods here is also this. So this is the proportion of good numbers, between 1 and n. The proportion of good numbers to p1, proportion of good numbers to p2, and so on all the way to pk. So if you multiply them, this tells you the proportion of good numbers to the entire product. All right, so hopefully this was clear. So I guess we will take a break here on Euler and Fermat's theorem. And in the next class, we're going to be looking at some of the more advanced concepts like Wilson's theorem, modular inverses, and things like that. Okay, thank you, everyone. Take care. Bye.